We introduced public key cryptography last lecture, and to demonstrate public key cryptography, we went through how this algorithm called Rsa works. And we went through the steps for generating a key pair, a public and private key for each user, and then the steps we went through an example of encrypting some message. So we'll go back to that example in a moment just to remind you, but first let's just explain what is Rsa. So it's the name of the algorithm, and the name comes from the three inventors, the three guys who created the algorithm: Revest, Ron Revest, Eddie Shamir, and Len Edelman, so RS and A. So they created this algorithm not long after the first public key algorithm was released by Diffie and Hellman. And you see at the end of these slides, we will not cover it before the midterm, we'll cover it after the midterm, another algorithm called Diffie-Hellman. But Rsa was an algorithm created, and they went and created a company that sold products that used it, including spin-offs that sold certificates for websites. So most of the certificates that we use today to access websites using HTTPS use Rsa. And some of the people who worked at Rsa Security spun off what was now become VeriSign, who's a major certificate provider. So it's considered the most widely used public key algorithm. There are others, but it's widely used, still considered secure, and it's not commonly used, though, for encrypting data. We'll see it's primarily used for authenticating. And we'll explain the difference after we go through the algorithm. So let's return to our example. Actually, we flick between the slides and the example. This is the algorithm itself. 3 steps, or 3 parts of the algorithm: generating the keys. You can think every user has a key pair. So every user generates their own key pair. You do it yourself. You don't get someone else to do it for you, because one of them is a private key. So only you should know that. In our examples, we've said the private key is those values of D and N, and the public key is E and N. But just be aware that the private key, the value of N in the private key is actually public. The secret value is D. It's just that we combine them together because when we encrypt, if we have some message M where we treat as an integer, as long as M is less than N, so our integer, the message we want to encrypt, must be less than N, then to encrypt we take M, raise it to the power of E and mod by N, and we get our ciphertext. And to decrypt, we take the ciphertext raised to the power of D and mod by N, and we get the original M back. And what we'll try and do today is prove that we always get the original M back, because that's a requirement for encryption and decryption, that we do get the original plaintext back, and that will lead to, well, why do we go through these steps of key generation? What's the significance of doing it in this manner? So we'll try and cover that today. The example we went through, we generated, in fact, 2 sets of keys, one for A and one for B. And we had an example where A wanted to send a confidential message to B. That message was 15. So again, if our message is some string, we need some way to convert it to an integer using some form of encoding under the condition that M must be less than N. And to send to B, we encrypt using B's public key for confidentiality, because the only person who can decrypt is the person who has the other key in the key pair. So if we encrypt with B's public key, it can only be decrypted with B's private key, and only B has their private key. So that ensures confidentiality. So what we did to encrypt, we took the public key of B, which is really E and N, 5 and 299, and 15 to the power of 5 mod 299 gave us the ciphertext of 214. We send that to B, and we showed when B decrypted, they got the original message 15 back. We need to prove that that will always happen today. And then we got to, well, from the attacker's perspective, what can they do to try and defeat the security of this algorithm? And we said the attacker knows the ciphertext, that's a given. They know the public key, E and N. So there are different approaches the attacker can take. The first approach we have tried as the attacker is we also know the algorithm. So we know this equation, C equals m to the power of E mod n. We know 3 of the variables in that equation. So the challenge for the attacker is to solve the equation, rearrange and find m. 2 different approaches to find m. You could do a brute force type approach and try m equal to 1, see if it gives us 214 when we raise to the power of 5 and mod by 299. If not, try 2, 3. So try all possible values of m. That would work, especially with our small numbers. So for the real use of RSA, we must have our numbers large enough such that that would not work, that we cannot try all possible values of m. That is, m must be potentially large, and the limit of m is n, the modulus. So n should be large. The other approach is trying to solve it by just inverting the equation. We have some exponentiation in modular arithmetic, and the opposite is discrete logarithm. It can be written as the discrete log. We need to find the base m. When we mod by 299, we get an answer of 215 when we raise to the power of 5. So we need to find m. And again, for large numbers, solving discrete logarithms is considered practically impossible. So as long as we use large enough numbers, there are no known solutions that will find the answer within reasonable time, within thousands of years. So solving discrete logarithms is considered a hard problem to do. So that's one reason why RSA is considered secure. Solving a discrete logarithm is a computationally hard problem. So if we couldn't try that, there's other approaches the attacker can take. They also know the message is equal to the ciphertext raised to the power of d mod n. In that equation, we have 2 unknowns, m and d. If we can find d, we'll find m easily. So the other approach for the attacker, find d. And again, since we know how the keys were generated, we know that some e times d mod the totient of n equals 1. That's the rule for generating the keys. So again, we have an equation. 5 times d mod the totient of 299 equals 1. We need to find the d. And 2 ways to find it. Well, to find it, we need to know the totient of 299. And 2 ways to do that. Factor the totient into its 2 primes, p and q. Once we do that, it's easy to find the totient. And then it's relatively easy to find d. Again, if we use large numbers, a large n, factoring it into its 2 primes is considered a problem which is also computationally hard. Meaning, if n is large enough, no one will be able to factor it into its 2 primes within reasonable time. So that's the other reason why RSA is considered secure. Factoring into primes is too hard to solve. The other approach is to manually solve the totient. By manually, I mean think of the approach try is 1 and 299. Are they relatively prime? 2 and 299. And count all the numbers relatively prime. And again, there are no known algorithms which are can be completed in reasonable time if n is large. Large, we'll give some examples of what we mean by large soon. So the security of RSA depends upon the fact that factoring a number into its primes is hard. the calculating the totient of a number is hard, and the solving a discrete logarithm is hard. And people consider them to be hard, and in fact the easiest of those three problems is considered to be factoring into the primes. And so when people try to attack RSA, that's what they try and solve, because that's the easiest one to solve. They try to attack it in terms of, given n, try and factor it into its primes. So prime factorization is a very important problem with respect to RSA security. Of course, with the small numbers, you can solve it and break RSA. And your quiz question and maybe an exam question will be, here's a public key, find the private key. I think that's one of the quiz questions. So you can do it for small numbers, but just be aware when we use larger numbers, it does not extend. It's not possible. Questions on RSA. That's a summary of what we got to last lecture. So we want to do two things. We want to say a little bit about the practical use of RSA now and how large the number should be. And also we want to explain or prove why did we get 15 here? Why did we get the original m back? That is, I started with a message m of 15, I raised it to the power of 5 and mod by 299 and get some number, 214. Now I take 214 and raise to a power of another number, 53, mod by 299. Why do I get 15 back? Why isn't it 16 or 17 or some other number? Well, if it is a different number, then the algorithm doesn't work. It was designed to work. So let's just look at, well, what is the design such that this will always work, such that it will always get 15, and that will lead to the key generation steps. Let me just check your notes and see if I've given you this. Sorry. Right, if you go forward a few slides on the from the handouts, there's another handout called Public Key Cryptography Examples, and what I'll go through is that first one, the Rsa Conditions. So there's no need for you to write it down. I'll show some of the conditions. So what do we know about RSA? We know some of the, let's write the encryption and decryption algorithms. And I'll denote the m that we get here first as m prime. The RSA algorithm tells us that we take some original message m and raise it to the power of e, mod by n, and we get c. And if we take that c and raise it to the power of d and mod by n, we'll get some other, let's denote m prime as output. We require m to be the same as m prime. We require the original message to be the same as the decrypted message. Otherwise, our decryption doesn't work. So the question is, under what conditions does m equal m prime? Well, before we look at the conditions, let's consider an example, and let's just choose, instead of going through key generation, let's choose some different values of some small numbers. And I'll let you choose. What's M? Give me an M, small number, easy to calculate. Less than 20. 5, someone said 5, okay. E? Let's choose any values, not follow the rules for key generation and see if it works. Okay, let's just choose these values and just see if it works. So what do we get? C equals our value of M, 5 to the power of 17. That number's too big, we'll use the calculator. Mod 20. What do we get? We'll use a calculator to solve that. Five to the power of 17 mod 20 is 5. Easy. That's the encryption. So C equals 5. Let's decrypt. M prime equals C to the power of D for mod 20. What do we get? Five. So it works. That is, the original message, M equal to 5, and the decrypted message, M equals 5, so that's what we expect. Let's try another one. So we need this to work. Let's try, say, N equal to 21. Everything else the same. I will not write it down. What will C equal? It'll be 5 to the power of 17 mod 21. 17. What does M prime equal? 17 to the power of 4 mod 21. What did you do wrong? 4. It doesn't work. So it doesn't always work. So we need to know what conditions will it work, and we must make sure that we choose values such that it will always work. We cannot just choose any value. Okay? And there you can do some analysis to why these two work. One worked and one didn't. But we'll go through and look at the conditions where it will always work. So it doesn't work, meaning we start with a plain text message 5, we encrypt and then decrypt, and we get a plain text message of 4. That's not good encryption if we don't get the original plain text back. So let's look at the conditions when it will always work. That is, we'll always get the same M as output. When does M equal M prime? Look at our equations. We can substitute in. Let's try. We said M prime equals C to the power of D mod n. But we know an equation for C, so let's replace that. From the top equation, C we said was calculated as m to the power of e mod n, all to the raised to the power of d, all mod n. All I did was replace the C with the first equation for the encryption equation. Just a substitution there. And we use our rules of modular arithmetic. We can expand this out, and the mod n can come out of the brackets, and it becomes m to the power of e to the power of d mod n, something to the power of something, all to the power of something is m to the power of e times d. That's just our rules of exponentiation. So, and I'll write m prime. So we're saying that for m to equal m prime, this must be true. Under what conditions? Or the other way to write it, so if m is to be equal to m prime, we must have, let's remove the prime now, we must have the conditions such that the message is equal to the message to the power of e times d mod n. We must have values, especially of e, d and n, such that this is true. And something equals m to the power of something mod n. Go back to our number theory. What are some of the theorems there? Fermat's theorem and Euler's theorem. Do they match that property? Their theorems told us about, for example, a to the power of something is equivalent to a mod n. And a hint, it's Euler's theorem. Have a look at Euler's theorem in your lecture notes, the second form. We wrote it as something like a will equal to or equivalent to a to the power of the totient of n plus 1 mod n. That is, Euler's theorem told us that if we have some integer a and raise it to the power of the totient of n plus 1 and then mod by n, we'll get that original integer a back. And for Rsa to work, we would like it to be of that form. That is, we take some integer m, raise it to the some power, mod by n, we must get the original integer m back. That's what we want. So this will be true if the black equation is of the form of Euler's theorem. That is when? If E times D equals the totient of n plus 1. If it was, you'd see it's in the exact same form. If you replace E times D with the totient of n plus 1, then it would be m equals m to the power of the totient of n plus 1 mod n. And we would always get our original integer back. So Rsa encryption and decryption will work if E times D equals the totient of n plus 1. Or E times D mod the totient of n should equal what? the totient of n plus 1 mod the totient of n equals, there'll be one remainder. Think 10 plus 1 mod 10 equals 20 plus 1 mod 20, 1. It's always one remainder. So the totient of n plus 1 mod the totient of n will be 1. So we can say, under what conditions does RSA work? Under the condition that E times D, those two values we use, equals the totient of n plus 1. Or, another way to think of that, E times D mod the totient of n equals 1. So the conditions for RSA to work so far are this last equation. We need an E times D mod the totient of n to be equal to 1. This is multiplication. So we need to have some conditions for that to work. What does it say about E and D? Something times something equals 1 in modular arithmetic. What do we call that? Right, and sometimes we call it a multiplicative inverse. Remember? An inverse in multiplication is when you times two numbers together and you get 1. So we say E and D are multiplicative inverses of each other. When are they multiplicative inverses? When they're relatively prime in the totient of n. So the condition is, for this to be true, we must choose values such that, I'll write it in brief form, that the multiplicative inverse of D equals E, vice versa, the multiplicative inverse of E equals D in mod the totient of n. That's the condition. When does a number have a multiplicative inverse? When that number is relatively prime to the totient of n. So our conditions are, we must choose an E which is relatively prime with a totient of n. If we do so, then we can find, if we know the totient of n, we choose some E which is relatively prime with it, then we know that it must have a multiplicative inverse. And there are algorithms for calculating what is the multiplicative inverse. They're not too hard. So if we know E is relatively prime with the totient of n, we can find D, and it meets this condition, E times D mod the totient of n equals 1, which tells us that E times D equals the totient of n plus 1, and that means our equation for RSA encrypt and decrypt matches Euler's theorem, and that means that we'll always get the original m as output. The m that we encrypt will be the same as the m we get when we decrypt. Where is this leading us? This is leading us to why the key generation steps are as they are. That is, we must choose an E which is relatively prime with the totient of n, and then we calculate a D. Go back to key generation. What were the key generation steps? Look at step 2. We'll get to step 1 in a moment. Step 2, select an E which is relatively prime with a totient of n. Here we denote it as greatest common divisor equals 1, but that's relatively prime. So that's why step 2 is that, so that we can successfully decrypt. Calculate a D which is the inverse of E. Why? Because The proof of RSA decrypting successfully requires that. Last step. If we're going to generate keys, we need to know what is the totient of n. So how do we choose a number n such that we can calculate the totient of n easily? We can choose it as 2 primes. If we, instead of choosing some n randomly, we choose 2 primes, p and q, where n equals p times q, that's a q, then we can easily calculate the totient of n. The reason for doing it that way, or a reason, is that we know when we generate the keys, instead of choosing an n, we choose 2 primes, and then finding the totient of n is easy. Then we need to find a number relatively prime with the totient of n, and then we can calculate d, the multiplicative inverse. What this is trying to point out is that the reason the key generation steps are these 3 values, 3 steps, is so that RSA works. If we used other steps, it wouldn't decrypt successfully. And we saw an example when we just chose random values or strange values of E and D. What did I use? 17 and 4 and mod 21, it didn't decrypt. We must correctly choose the values. Any questions?
About the trapdoor.
The trapdoor.
Sometimes it's easy to encrypt, but hard to decrypt back.
Right, and we'll come back to, we'll talk in generally that this algorithm, RSA, uses mathematical operations which are easy to do in one way, but hard to do in the other way, called a one-way function or sometimes a trapdoor function. And for example, it's easy to calculate the totient of n if you have p and q. But it's hard to calculate the totient of n if you don't have p and q. You need to just go from the actual value. That's an example. This is maybe a little bit too much to go through on an afternoon close to 4 o'clock. There will not be a question in the exam about proving RSA, okay? So there'll be questions about RSA, guaranteed, how to generate keys, encrypt, decrypt, some other questions, but not what we've just gone through there of proving why it works. I have asked that in previous exams, but not this year. I'll create a harder question instead. No, not harder. Let's go back to our slides and see what we've got. So we must generate the key using these steps. Those steps were chosen such that the decryption would work correctly and such that it will be secure. So those requirements we went through, well, let's summarize again. The steps are chosen so it's easy for us to find E, D, and N. That is, we can use a computer to choose a value, choose the 2 primes, P and Q, calculate N, find E, find D. A computer can do that quite quickly for us. We need the algorithm has the features such that it's easy to encrypt. That is, if I take some m, raise it to the power of e and mod by n, my computer can calculate it quite quickly. It doesn't take years to calculate. And similar, it should be easy to decrypt if we know d, and it meets that. But it must be impossible to find d given e and n, and we've gone through why that's the case. And we'll summarize that later. And the conditions for it to work are listed there, which we've just gone through. We've gone through an example of RSA. We'll return to this a little bit later. Now let's look at some of the practical aspects. Our example used small numbers, just so we can do it in our head. what should you use in practice? Well, it turns out we use very large numbers. How easy is it for RSA to compute, to encrypt, decrypt and generate the keys? Well, some things that it takes advantage of is modular exponentiation. Remember, we take, let's go back, the algorithm. Let's say m is a large number and e is a large number, or if the ciphertext is a large number and d is a large number, you take one large number, raise it to the power of another large number, what do you get? A much, much, much larger number. Okay? So that can be slow to compute, and then mod by n. So that can be slow to directly compute. So implementations of RSA take advantage of the fact that we can expand that down, that this property of multiplication, that is, we can break it into steps which make it easier to compute in a computer. So there are ways to make RSA faster than just directly doing a large exponentiation. What about choosing the values? What about E? Remember, we chose E, relatively prime with the totient of n. What value do you choose? It's a public value, and there are some values which are widely used. Because it's public, you don't have to have a different value from someone else. The D value must be different because that's private, but the E value can be the same as other people. And it turns out that implementations often use the same values. So some examples are 3, 17, and a common one we'll see is 65,537. People have done analysis and found out that these are suitable values of E, and that they make doing the exponentiation quite fast. Raising our power m to the power of E, if E is small, then it's quite fast to do. And these can help with the implementation. There's some special attacks that if you do use a small value of E and you use an inappropriate or small value of m, then attacks may be possible, but they're very easy to overcome to make sure m is large, add some padding to it. So if m was quite small, you should, or the software that encrypts for you should make it larger such that the attacks are not possible, and that works quite well. D is your private value. Of course, that needs to be large because someone can just try and guess it. If D is small, then they can do a brute force attack and try all possible values of D until they get the right value. So it needs to be large. But if it's large, we're taking a number C and raised to the power of a large number is slow to compute. There are ways to compute the decryption quite quickly. So the Chinese remainder theorem and Fermat's theorem makes it, again, easy to compute even for large values of D. We'll show you some examples of how long it takes shortly. P and Q are very important. They must be large, very large primes. Why? Because you get n from multiplying P and Q, and the challenge for the attacker is given n, find P and Q. And it's only hard to find the prime factors when that number n is very large. So P and Q should be very large primes. Generally what's happened, there are algorithms to choose choose primes for you that usually just choose a random odd number and do many tests and check that it is prime. It works most cases. So the strength of RSA, a brute force attack, an attacker can try all possible values of D to try and guess it. Well, to stop that, make sure D is large. But a large D makes the algorithm slower. And we've gone through these mathematical attacks. 3 things the attacker can try to do. Factor n into its primes. Calculate the totient of n directly without knowing P or Q, or do a discrete logarithm to find D without even knowing the totient of n. So there are different attacks that they can do in theory. All of those require solving computationally difficult problems. So long as the numbers are large enough, the attacker can't solve them. Of those approaches, factoring n is considered the fastest or the easiest for the attacker and is a way to measure RSA security. There are some other theoretical attacks, timing attacks, chosen ciphertext attacks. So there are other known attacks on RSA which can be successful, but they're very easy to defend against. So there are countermeasures which are commonly implemented. So in theory there's an attack, but it's very easy to prevent the attack by adding a few modifications to when you encrypt and decrypt. How big should n be, or how big should the two primes be? This is a little bit old, but it's RSA, the company who released products that used RSA, they want it to be secure. They used to, in the past, have a competition that you'd win thousands or hundreds of thousands of dollars if you could factor a number n into its two primes. And some of the winners of that competition, so back in 1991, n, which was 330 bits, so 100 digits. If you write a number 100 digits, if that was the value of n, back in 1991, people eventually factored that into its primes, p and q. And the competition was extended, and the most recent one, it's been closed, but in 2009, some group factored a 232-digit number n into its primes. So given some n, they use many computers and some specialized algorithms to find the two primes p and q. It took about 2,000 years if you used a single computer to do that. So they used many computers, of course, but the equivalent to you running one computer, in that case a single core computer, for 2,000 years to factor that 232-digit n into its primes. Making n larger, of course, makes it harder. And the typical values of n when RSA used are these three values: 1024, 2048, or 4096 bits. And 1024 bits is still considered secure. But for safety, people recommend nowadays using 2048 bits. But there are no known attacks on 1024-bit values of n. So in fact, this is the value of the modulus n in RSA. It's usually set, and the p and q values are set such that we multiply together, we'll get this 1024-bit or 2048-bit value of n.
So right now there is no report on any people can factor out the 2048 bits.
There are no known successes in factoring a 2048-bit value of n into its primes, and similar for 1024-bit. Okay, so even there are no known attacks on 1024-bit. It's still considered safe, but maybe in the short future, maybe people do get to factor 1024 bits. Therefore, it's recommended to use 2048 bits just to be safe.
Back in 2009, 716 already successful, so it's close to 1,000 already.
Close to 1,000, well, be careful. You're increasing, it's another 200 bits or so. So just adding bits doesn't, it's not linear, okay? That is, the strength, adding bits can make it much more stronger, okay? And so you cannot simply extrapolate from here, but if you did, what have we gone? We've gone over 18 years, increased by 400 bits, okay, from 1991 to 2009, increased by about 400 bits. Well, if it was a linear, then another 18 years in what, 2027, maybe would get up to 1,000 bits. But if we're already using 2048 bits now, then that's still considered safe. Okay. But in fact, it's not linear like that, but still people consider 1024 okay, but no longer recommended just to be safe. But many people still use it. We'll look at two examples where I'll use, first case I'll use some software just to generate some keys, and we'll look at them and see the actual values, and then I'll show you another realistic example of RSA keys. Before the examples, because that will finish us for today and this topic, because we will not go on to Diffie-Hellman, but let's just go back to the start and see what slides I've missed over here. So just recap on the principles of public key crypto systems. We've gone through the history. We know that we have a public and private key pair. This is in general, not just for RSA, but for other algorithms as well. There are others. And we've seen that for confidentiality, use the destination's public key. Always remember that. And there may be, I think, some of the quiz questions. One of the quiz questions is something about in which order do you use the keys. For confidentiality, to keep a message secret, encrypt that using the destination's public key, such that the only person in the world who can decrypt is the person who has the corresponding private key, which should be the destination. But we can use the keys in the opposite order for the purpose of authentication. I want to send a message from A to B. I don't care if someone else sees the message, but I want to make sure at B, so B wants to make sure that this came from A. It didn't come from someone pretending to be A. That's authentication in this case. So A will send a message to B. We don't care if someone sees the message. Anyone's allowed to read the message. But B wants to be able to prove that this message did come from A, not someone else. And that the way we do it is that we encrypt the message with the private key of A. If we encrypt with a private key of A, what can we decrypt with? The other key in the key pair, which is the public key of A. That's the only thing that will successfully decrypt. So we encrypt with the private key of A, send the ciphertext, the encrypted message with the private key of A to B. What B does is verifies the message. And to verify, they decrypt with the public key of A. Of course, they know the public key of A, it's public. So B uses the public key of A to decrypt. And B checks. If it does decrypt with the public key of A, that implies it must have been encrypted with the private key of A, and that implies that this message came from A, because there's only one person in the world who has the private key of A. So this is a form of authentication. Can someone else, maybe the malicious user C, can they view the message M? What do they need to do to see the message? You're an attacker now. What will you do? You want to see the message. How will you do it? Come on, put on your black hats. Think about what you'll do. Use the public key of A. Right? You can see the message. The message was obtained, we encrypted the message with the private key of A to get the ciphertext. So if the attacker knows the ciphertext C, then they can of course decrypt with the public key of A because it's public. So this does not provide confidentiality. Everyone can see the message. That's not our purpose here. Can the attacker send a message pretending to be A? How do they do that? If I send a message pretending to be A, I need to encrypt that message with some private key. If I use it, of course I don't have the private key of A, because that should be private to A only. So if I'm the malicious user C, and let's say I encrypt the message using the private key of C, send it to B and tell B this came from A. What does B do? It tries to decrypt with the public key of A. If B thinks the message came from A, then they'll try to decrypt with the public key of A. But since it was encrypted with the private key of C, the malicious user, it will not successfully decrypt, and B will know that and therefore not trust the message. So this provides authentication. If someone tries to send a fake message pretending to be from A, they must encrypt it with some private key. The only one that will work is the private key of A. And the only person who has that is A. So that implies that A sent the message. Similar, it can be seen if you try to modify the message along the way. If you try and change the message, that is, you intercept the ciphertext and try and change the message somehow, then you need the private key of A to send the encrypted form back to B, and since you don't have the private key of A, you cannot modify the message either. So public key cryptography can be used for confidentiality, keeping a message secret, or if you use the keys really in the opposite direction, encrypt with your private key. Then it can be used for authentication, proving who the message came from and ensuring that the message has not been modified along the way. And after the midterm, we'll spend more time on authentication, this technique and other techniques for authentication. But that's just a brief introduction. I think that's all we need to say. That compares conventional or symmetric key cryptography and public key cryptography. There are different algorithms for public key crypto systems. RSA we've gone through. Diffie-Hellman will go through after the midterm. There are others as well, elliptic curve cryptography, digital signature standard, which we'll not go through, but there are others that are possible. Some are used for confidentiality, encrypt and decrypt for a secret message. Some are used for authentication, and later we'll introduce the name for that is a digital signature, but not yet. So signing a message, actually we can say, this process is called signing a message. A signs the message using their private key. Same as you sign a document using your own signature, your own handwriting. Here you sign a document or a message using your own private key. So we sign a message using a private key in public key cryptography. I think there's no need to go through this at this stage. This is just states some of the requirements of the general algorithms, but I think we've mentioned them along the way, especially with RSA. And this talks about the trapdoor function that the algorithms must have, but again, this is general for all algorithms. We've seen a detailed example for RSA, which is sufficient for this stage. So we're focused on RSA for public key cryptography. We'll finish today with an example of RSA, and that will finish this topic for up until the midterm. What was the previous homework? Everyone did that? I haven't marked it yet. What is the homework? OpenSSL. Okay, right. You used OpenSSL to encrypt. So let's use OpenSSL. You used it for AES, triple DES and other algorithms, symmetric key algorithms. It can be used, of course, for public key algorithms. So I'll not use it for encrypt, I'll just simply use OpenSSL to generate some keys. Quite simple, I'll just copy some commands to generate some keys and then explain. Let's hopefully I get it right. Let's just explain this command. Right, we're using this software that you've been introduced to called OpenSSL. Note that OpenSSL is, it's really developed as a library. So that the applications that you write can call the OpenSSL library to do cryptographic operations. So that your application doesn't need to implement RSA or AES. You just call OpenSSL to do it for you. But it also offers a command line interface. But the main use is as a library for other applications. Generate public key pair. That's the operation to generate a key pair. The algorithm we're going to choose is Rsa. And for this case, I'm just illustrating some options. We don't need them, but there are some default values. But a public key option for Rsa, the bits, we're generating a 2048-bit value of n. So we could have specified 1024 or 2048 or 4096. That's the length, so the strength. And in this case, the value of e, what's called the public exponent. The exponent we raise to the power of e. Let's use 3. So e, we'll use 3. It defaults to some other value. And the output will be put into this file, which I've called, let's change it to key pair. Just a file that stores it. And it's of a particular format that's commonly available for exchanging key pairs or parts of keys. It took some time. Okay. You time it. Or we can time it. It takes real time 427 milliseconds to do that. Okay, well, it seems fast, but in fact, compared to some other algorithms for generating a random key for symmetric key ciphers, it's actually slow, but not a problem. So performance-wise, it's fine. It does take some time on different computers because it needs to generate 2 large primes, P and Q. And it goes through an algorithm to generate and test, does it really have large primes, P and Q? That takes some time. So it prints some output just to indicate that it's doing something along the way. Let's have a look. So the key pair is a file. It's formatted in such a way, it's 1700 bytes. Let's have a look. I may have to zoom out. It's a text file, but it's formatted in a way that it's encoded. Yeah, don't look. This is my private key. We'll explain the details. So it's encoded in some way such that you can easily copy and paste it into an email or save it as a text file. But actually, it contains multiple values. Should contain in there somewhere E, N, D, and some other values we'll see in a moment. So we'll just view that in a nicer way. And I'll just take that key pair in and output it as some nicer formatted text. And then we'll scroll up and see. So this is a little bit nicer format. Let's just look through the values. So it gives the raw format, and then the software interprets the actual value. So here's the modulus. The modulus is n. Remember, mod by n. It's 2048 bits long, the modulus, and those bits are here given in hex. So this is the actual value of n given in hexadecimal. Down the bottom is e. The public exponent, remember we raised to the power of e, 3 in decimal. So e is very small in that case. And here's the one you shouldn't remember, is my private exponent d. The private exponent is d in our equations. That's long. And remember, we require d to be large because we don't want someone to be able to guess what my d is. So it's also about 2048 bits. So when the algorithm works, it chooses the value such that d is about the same length as n, a little bit shorter. So d is about 2048 bits. So to guess that, you've got 2 to the power of 2048 possible values, and you cannot guess that in reasonable time. And actually it stores mainly for performance reasons, it stores some other values. The primes, p and q, prime 1 and prime 2. So there are the 2 primes that were used. So it generated p and q, it calculated n, the totient of n, and found e and d. And the last set of values we will not cover in any depth. Exponent 1, exponent 2, and the coefficient are 3 other values, again just included for speeding up computations. You can speed up the encryption and decryption by storing some intermediate values, and these are stored in my key here. On the lecture slides, this slide lists the names of those things that we see from OpenSSL. So the modulus is n, the public exponent is e, the private exponent d, the 2 primes p and q, and these other 3 values are related to d and p and q, and they're only used to speed up encryption and decryption, to make it faster. And we consider all of those values to be my private key. So they are the values I must store, and I store them all together. Of course, some of them are going to be public, the first 2. N and E, I'm going to tell other people. But I would normally store them in a file, like the file that I have just generated, all those values, such that when I can want to encrypt something or decrypt something, I have those values all in a file. Last thing for this one, we can extract the public key. If I want to send my public values to someone, we can do so. That just takes all of those values and puts into a new file just the public values. And this just shows those public values. It shows that the 2 public values are the modulus n and the exponent e, which is 3. And this is the file which I can make available to others. So, of course, I keep my private key private, and the public key I can put in an email, put on a website, but use some mechanism to make available to others. So we can generate keys quite easily. Maybe in a later homework after the midterm, I'll give you some tasks for using OpenSSL to generate keys and encrypt and decrypt, and you'll see some performance measurements. The last thing, you have a midterm exam coming up, but even before that, we visit a website, and you know you use HTTPS for secure websites. And if you click on the little icon, the padlock up here, it tells us something about the encryption used for when my web browser accessed that website. And it gives us some more information, and we'll cover this in a later topic a little bit more, but it uses certificates. Okay. And some technical details here. It may be hard to see. if you cannot see, it says down here TLS. TLS is the protocol used by HTTP for secure connections, the transport layer security. ECDHE. EC stands for elliptic curve cryptography. We're back. That's a public key algorithm. DH for Diffie-Hellman. So there's a combination there. We haven't covered them yet. But it uses RSA in here for the certificate. And it actually uses AES to encrypt the data, a 128-bit key of AES, using some mode of operation called GCM, one we didn't cover. And it uses SHA-256 as a hash algorithm, which we'll cover after the midterm. So to encrypt my connection, and not only to encrypt the connection, but for me to prove, or my browser to be sure that I'm accessing the right website, we use different cryptographic algorithms, and RSA is a key one, an important one in there. If we view the certificate and we look at the details, again, hard to see. You'll have a look in your own browser to see all this. But we see in here the public key algorithm used in the certificate is RSA. And the subject's public key is given here. The modulus is 2048 bits, and the exponent is E, 65,537. This is the public key of the website that I visited. And that's used to support securing the connection between my browser and the website. So RSA is widely used in web security. And in a later topic in this course, we will look into more detail of what a certificate is and how all those algorithms come together. That finishes this topic. Any questions?